All right, hello everybody. Thanks for coming. Sorry for the slight delay. I want to talk to you today about question answering for language and vision, computer vision, and this is mostly focusing on the work that Kai-Ming Xiong and Stephen Meredy have done in the last couple of months, and will actually be presented at ICML next week. So I want to start with what may be a contentious question, maybe less so in this workshop, given it's a QA workshop, but in some ways, I wonder if we could reduce or convert almost all NLP and maybe even AI problems and tasks into question answering, which is questionable. So let's look at maybe a couple of examples of what I mean by this. And these are examples of input question answer triplets. Basically, the first one is what we would traditionally see as question answering. You have a couple of facts, and this is an example from the Bobby data set, which we discussed and Jason introduced in the previous talk earlier today. And we would basically suppose the model needs to logically reason and find, Sandra took the milk there, do some anaphora resolution, find out what there means, and basically give, in the end, the right answer, hopefully, which is garden. But we can also see the input as, everybody's happy, and the question is, what's the sentiment? And the answer should be, it's positive. And you can go to sequence level task and ask, what are named entities or what are the part of speech tags, and you would ideally have an answer for every single word to, answer these kinds of questions. And you can go as far as saying, what's the translation into French, and then you would ideally have an answer sequence that actually is that sentence in a different language. And so that's not a very useful abstraction until you could actually find either a single architecture or maybe even a single model which shares all the weights to tackle all these different kinds of questions. And for now, and in this talk, I'll only focus on a common model architecture for these different kinds of QA problems, and I'm not focusing yet on a single model where all the weights are shared. So this is just a single architecture, and then step 2 would be actually combining these different ones into these different QA problems into one data set and one model. Basically, this original idea led us to eventually think about and come up with dynamic memory networks. And we hope that this can be seen as an architecture for a whole variety of different QA tasks. Let me ask here, who is familiar with GRU and RNNs? Awesome.
Just from the last session.
All right. So I guess there's still a third of folks who aren't. Maybe I'll walk through it really quickly. Who here is familiar with word vectors? Almost everybody, right? All right. I assume the last few of you who didn't raise their hand just are tired. So let's assume you have a word vector at every time step for every word, and you have a sequence model, and you have from x from 1 to t, you have a word vector at each time step, and then you basically have a sequence of neural network layers. This W here is just a matrix, so you have a matrix vector multiplication, and you basically want to compute at every time step, so for every word, given the current word vector and the previous time step vector, you want to compute your current time step vector. And you'll do this by having here a single layer neural network. So this will be called our update gates. And we'll basically sum up just these two matrix vector multiplications and a bias term. So this will basically give us a list of numbers, a vector with numbers between 0 and 1. We have here the sigmoid that just squishes any real number to be between 0 and 1. And we'll do this twice, but with different sets of weights, W here. And now where the GRUs come in and become powerful is with these element-wise multiplications. So the reset gate here intuitively basically will allow us to ignore all the past time steps. So we could have done the same thing. So in fact, if the standard recurrent neural networks just have this equation in their entirety without the reset gate, but then you would basically update your current hidden time step for every word in some really fundamental way. And if you will always take into consideration the past time steps. What this will allow you to do is essentially say, well, maybe the past doesn't matter. Let's say you have, for instance, sentiment analysis. You can basically say, here's a whole synopsis of the story. And in the end, you say, and now I'm going to talk about whether I really like the movie or not, and I thought it was awesome. Right? That kind of example can be tackled if these reset gates are all numbers that are very close to 0, and then all that matters is that you set awesome. And awesome will now change your hidden state a lot. And all the past sort of standard plot talk won't. So that's the idea of the reset gate. So if it's close to 0, you can basically ignore the past. And now the update gate Z is similar, but in the opposite way in the sense that it can ignore the current time step entirely. So if Z, again, a vector of lists of numbers, vector of numbers, all between 0 and 1. And these are all vector operations. So Z is a vector, HT is our previous hidden time state vector. 1 is here a list of ones. And this is just element-wise subtraction and element-wise multiplication with the Hadamard product here. And now if ZT is all ones, what that basically means is we're just going to copy over the previous hidden state. And so it's sort of the opposite of the sentiment story, for instance. Maybe the things at the current time step don't matter. You're just talking about the plot. But you had mentioned that the movie was awesome in the beginning of the review, for instance. And so all you can do here is copy over your hidden time steps and ignore the inputs at the current time step. All right, that was a short crash course in recurrent neural networks and gated recurrent units. We have here actually the inventor, maybe somewhere in the room, Joe et al. All right. So now let's look into the actual dynamic memory network architecture. And this plot is a handful. Don't worry, we'll zoom into all these different modules. I think there are two main takeaway messages. The first one is, I think as we build more and more complex models, it'll be good for us to try to use good lessons from software engineering and try to modularize the different aspects of our machine learning systems. And in a perfect world, these different modules will communicate in a principled way, and such that in the end, you're actually able to train all of it in an end-to-end fashion. So here, we'll have some input, we'll have some question, we'll have some way to mull over our input conditioned on this question, and in the end, we want to produce an answer. And that answer will be a simple softmax or logistic regression type classifier, but it will backpropagate through everything in this network and basically modify all these different modules. So let's go through a simple example of what this model would do with a specific question. So let's say the question here is, where is the football? And what this model now will do is it will have a representation for this question, a vector. And with that vector in mind, it will go over the inputs and pay attention to everything, every sentence that seems relevant for the current question at hand. So, for instance, where's the football? Well, the sentence, Mary traveled to the hallway, doesn't seem relevant. And so the gate and attention will be close to 0. But the sentence, John put down the football, that seems very relevant. So we would assume that that gets a lot of attention, the maximum amount of attention with 1. And then we have here in the episodic memory another sequence model that basically just agglomerates the relevant facts. But relevance changes over time, right? When I asked the question, where's the football, any fact of where John walked yesterday didn't seem relevant. But now that we connected John with the football in this sentence, maybe now this vector captures, well, you should also start thinking about John when you're trying to answer the question where the football is. And that's exactly the task of the episodic memory module, which will agglomerate the relevant facts in this vector M. And then, and this is sort of the main insight, we'll just repeat that process. We'll go over the inputs multiple times until the model thinks it has actually enough, it has agglomerated enough information to be able to answer the question. And so in our specific case here, now that it figured out that John is relevant to answer the football question, it will go over the inputs again and pay attention to John moved to the bedroom, and then John went to the hallway, and that was the last fact that was mentioned. It is able here to ignore other kinds of things through a mechanism we'll talk about very soon. And basically, in the end, agglomerate all the relevant facts, mainly the hallway for this one, into the vector M. It'll give that to an answer module and produce an answer. All right, so that's on a very high level what this model does. Conditioned on a question vector, pay attention sequentially to a bunch of facts, And if you don't think you know enough from doing that once, do it multiple times and multiple passes to eventually agglomerate enough, give that to an answer module, and produce an answer. So now let's zoom into the different modules. Fortunately, now that we know what GRUs and RNNs are, those are essentially all just recurrent neural networks. So this one is a recurrent neural network. In the simplest form, each word is a vector. And we'll just have basic access to end-of-sentence vectors in that long sequence of words. And it's just a GRU. The question vector will also be computed simply with a GRU. We have word vectors, VT, and the previous hidden time step at each of the word vectors for the question, and we'll compute the question vector. I will often drop the index here at the end and just Q as the final state of that recurrent neural network sequence model for the question. Now, the interesting stuff happens in the episodic memory module. I described the GRU as having this power to ignore and copy facts depending on the inputs, but it does that per element of the vector. And for these kinds of high-level QA tasks, it's better to have the ability to actually ignore sentences entirely if they don't seem relevant. And this is what this does. Basically here, we'll compute gates. I'll define those in the next slide. The idea here is the gates, these are these numbers here. They're single numbers, not vectors. If the gate is very large, then we will have a GRU and we'll input this current fact at that time step into our GRU. But if the fact doesn't seem relevant and G is close to 0, then all we will do is basically copy over the previous entirety of the previous vector. Are there any questions about this mechanism? Cool. All right. So how do we compute these gates? Well, it's relatively straightforward. We basically want to capture a couple of similarities between facts. So I here, these Fs are the facts, the sentence vectors that we have. And we want to compute how similar are those sentence and fact vectors to our question and our memory. So for instance, first, originally the question includes something about football. So if the fact includes something about football, the element-wise multiplicative similarity measures here, and distance and absolute value of just the subtraction here would be assumed large. And then later on, we'll agglomerate facts into our memory state. And then hopefully there we capture, oh, John was mentioned now. So intuitively, if the facts are similar, and so the facts mention John, the memory mentions John, you hope that some of the dimensions there capture high similarities. But it's all kind of fuzzy, and so we can't assume that it's this exact element of the vector that would capture these. So we pipe it through a standard two-layer neural network and then have a softmax at the end to basically focus the attention on a couple of the facts that seem relevant. So in the end, when the end of the input is reached, the relevant facts are hopefully summarized in this vector M. And we'll have another GRU that goes from 1M for the first episode to M of the second episode, and so on. So that's basically the episodic memory module. Now, there are two options. You can actually train the model to decide when to end the series of episodes, the series of iterations over your input. But you can also actually just say you always have 3 or 4 passes over your input, and that's it. At the end of those 5 passes, or n passes, you basically have to produce the right vector to give to the answer module. Then the answer module is also just a GRU. So notice how it was really here the most basic Lego block. You have recurrent neural networks. You have them in the input module, the question module, slightly modified version in the episodic memory module, and now also in the answer module. And the main twist here is that you will give as input at every time step the concatenation here of the previous output that you gave, the first word of the answer, y, or the previous word of the answer, and the question vector, as well as the hidden states. So the hidden states of the answer module are defined here as a sub t. And then in the end, you just have a standard softmax, just a different word for logistic regression classifier. So basically, in the end, you train this with standard cross entropy, but now because all of these vectors can be, are also parameters and computed through other neural networks, you can train that whole model end to end all the way to the word vectors that you could even initialize randomly. So there's a bunch of related work. The two main papers of this talk are these two, both at ICML next week. And then there's a lot of amazing work in general in sequence learning and deep learning. I encourage you all to check out these papers if you haven't already. And I think the most relevant work is actually from Jason here on memory networks and end-to-end memory networks. We'll compare to those in the next couple of slides. I think on a high level, the main difference is that we're trying to use the same basic Lego block, namely recurrent neural network architectures, for all these different mechanisms: the input representation, the attention mechanism, and the response mechanism. And that enables us to have, I think, a slightly broader range of applications that include sequence tagging, for instance. The main difference for sequence tagging is that the answer module will be not just triggered at the end of the inputs, but at every time step. So let's look at a couple of results. So this is the Bobby 1K dataset. I know there's been some discussion before. This is when we actually supervise the gates. So we tell the model, these are the relevant facts during training time, but not at test time. And I think this is the most accurate model still on 1K with gate supervision. Now, a lot of folks moved away from gate supervision because it would be much more powerful if we can just give it the question answer input triplets and not have to say, these are the facts that seem relevant for answering the current question, right? You just give it a Wikipedia page or something like that and would eventually focus its attention on the right things. And so this is the Bobby variant where you have 10,000 examples per question type and you don't have any gate supervision. We compare here to end-to-end memory networks and the neural reasoner with some original auxiliary task by Peng et al. And think that this is now also the most accurate model for Bobby 10K. But it's a very fast-moving field, so maybe it's changed in the last couple of weeks. A lot of NIPS papers are coming out now. It can basically do a lot of cool things like yes-no questions, counting, lists and sets, simple negation, and so on. But I also understand that this is only a synthetic data set, and it will be cool to see if we can actually apply that same idea and live up to that idea of trying to have a single architecture for a whole host of different kinds of tasks. And so this led us then to run a couple of other experiments. The first one is sentiment analysis. And what's kind of cool is that with the same general architecture, though, to be honest, like slightly different hyperparameters, right? Different sizes of the hidden states and all that. So it's, again, not the same set of weights, just the same kind of architecture. We also got the best accuracy on the Stanford sentiment tree bank. So getting closer to 90% on some pretty interesting examples. And I'll show you some of those in the next slides. But what's interesting is you might say, well, how much does that whole episodic memory actually help? And so the answer is, for some tasks, you really need it. So if you have transitive reasoning and you have to basically do if A then B, and if B then C, and if C then D, those kinds of facts that you can only pay attention to after you realize that new facts, new information that comes up seems important, you really have to have multiple passes over your input in this episodic module. And if you don't, then there are certain Bobby tasks that you just fail, and you cannot solve them. So if you have 3 supporting facts, or you have to count a couple of different items, then you really have to have multiple passes over your inputs. For sentiment analysis, the story is slightly different. Actually, the accuracy kind of reduced after having 2 passes over the input. And so let's look at a couple of fun examples on sentiment that basically the DMN that is already very accurate. It's one of, it's a very accurate model. But if you only give the DMN a single pass in the episodic memory module over your inputs, you get, these are examples where the DMN with 1 pass gets it wrong, and with 2 passes, it actually gets it right. And we'll often observe here that you can think of the first pass as getting a global sense of the sentence. And once you have that, then you can start paying attention to the right things. So here is, in its ragged, cheap, and unassuming way, the movie works. in the two-pass DMN, basically isn't quite sure, but pays mostly attention to unassuming. In the second pass, it really focuses on unassuming. It takes weight away from cheap, which is sort of the most negative thing, and really pays attention unassuming and works. It just works. And so in the end, it gets it right that this is actually a positive sentence. Here's another fun one. The best way to hope for any chance of enjoying this film is by lowering your expectations. And those are the kinds of examples that we're now working on in sentiment, right? You can, if you just want to get to like a good baseline system in sentiment, you just use naive Bayes with bigrams and SVMs, and you'll get to sort of the high 70s. But if you really want to find the soft nuances and the tricky examples and snarky comments and things like that, this is only when this kind of model shines. And so here it really pays in the end attention to the expectations, and it increases also the weight for lowering and realizes this is in the end negative. And here's the last one. My response to the film is best described as lukewarm. In the first pass, best is such a positive word. If you were to train a unigram model with most any kind of architecture, best would be very, very important. And indeed, the first pass, it is the most important word. But in the second pass, I actually realized, well, based in this context, it's actually being used as an adverb and not an adjective. You actually lower its weight and you increase immensely the weight on lukewarm and realize in the end that this is negative. So those are the results on sentiment. Now for part-of-speech tagging, where again you trigger your answer module at every hidden time step of your episodic memory instead of just at the end, you get a very accurate model too. I think recently there are a couple of new papers that come out. POS has been pretty well done task. That data set is over 2 decades old, so I wouldn't over-index too much, but it's a very accurate part-of-speech tagger as well. And then we had a new researcher join us, Tsai Ming, and he said, well, I like, he was a Vision postdoc before, and he said, well, I would like to see if the DMN can work on visual question answering. Because I was all like, everything is question answering. He's like, well, let's see if it actually works. And so he basically took literally the code that we had from textual question answering on Bobby, and he came up with a new input module that would give us, again, a sequence over stuff, over, in this case, images, and then ran the experiments. And without going into too many details here, input module is a CNN where you get little vectors, not at every word vector, but at every block of the image. And then you'll have a bidirectional GRU again that goes over all these little blocks in the image and the feature vectors that you get from a CNN. And what was kind of cool is we submitted it to the Microsoft server, and we're #1 right away, which was pretty cool. So it is actually quite general and even works for visual question answering. Can count in a couple of different things. I was still a little skeptical, and I think these are the last couple of slides of the talk. And so we tried to visualize the gates. So just like we can visualize the gates on words for sentiment analysis, we can visualize the gates on the images. So here is basically what you see in bright are the areas where the model learned to pay more attention to conditioned on the question. So again, just little weights of these gates. And the first question is, what is the main color on the bus? And it actually pays attention to the bus and says blue. I'm like, okay, it's kind of the main object. I'm still not quite convinced. Similar here, background, well, it could just kind of pay attention to stuff that is on top of the image in many cases. How many pink flags are there? Okay, it does pay attention to the flags. It's like warming up a little bit. Is this in the wild? It kind of pays attention to the background here and the building in the background saying no. And here I was like, this one I think we sort of got lucky. Who is in both photos? I strongly doubt the model actually understands that there are 2 photos and then matches them and so on. It's just like the main object or entity in that entirety, the entire image is just a girl, so it probably just outputs girl. But then there are a couple where I'm like, okay, this just cannot be random anymore. So like, what is the boy holding? It pays attention to the arm. to this arm, and then to this thing right under the arm, and it says surfboard. So I'm like, okay, maybe there's something here. Then, of course, there's one question and one worry that people often have, which is, well, if you just trained a language model, and just from the language alone, maybe you would know. So there aren't usually that many things that people can hold, right? You wouldn't say boat ever, even if you didn't see what the image was. And if you might ask, what color are the bananas, then without looking at the image, you might just say yellow, because you just know bananas are usually yellow. But then here, it actually did pay attention to the bananas, and it gave the right answer green, because they're not ripe yet. I was like, and there are a couple of cool things. So here's what is the pattern on the cat's fur on its tail. Pays most of the attention around the tail, and actually it said stripes. So I think there are a lot of cool things. We then built a demo and had some folks go at it. And one journalist wanted to really make it fail, and so he asked some questions. And I was like, I came up. One of the questions he asked, like, is the girl wearing a hat? And I was already coming up with excuses. I'm like, well, the hat's kind of hard to see. It's black and black background and so on. And then eventually it actually got it right. And surprisingly, once it really learned about the domain, it can do a lot of things quite well. So what is the girl holding? A tennis racket. What's she doing? Playing tennis. Is the girl wearing a hat? Yes. What is the girl wearing? Shorts. Of course, here you see, well, she's wearing lots of different things, but it's not giving us a list. So here it actually was trained to only give a single word as answers. Just because the data set, like 95% of all the things in the data set have a single word as the answer. And then these are interesting questions because you can, you change one word, like what is the color of the ground versus what color is the ball. And so, learns to pay attention to ground versus that tiny little area in the ball. What color is her skirt? White. And what did the girl just hit? A tennis ball. And so there's one question that eventually I got it to fail, which is you can ask, did the girl just hit the ball, or is the girl about to hit the ball? And it says yes for both times. So it doesn't quite have all the sort of statistics for the different movements. All right, so hopefully I could show you that indeed a lot of different kinds of NLP tasks can be reduced to question answering, and that the DMN is a model that can accurately solve a variety of different QA tasks. I think an exciting next goal will be to actually try to train a joint multitask DMN with the same weights, and we'll still need a bunch of people to join us to do that. All right, thank you.
Attention converge if you keep doing more and more episodes over it? Is it stable? Or does it keep changing?
Unfortunately, it depends on the task. So the question is, does the attention converge? We see here that, for instance, for sentiment analysis, if you go too often over the inputs, at some point it actually goes down in accuracy for sentiment. But on some of these Bobby tasks, I think that's sort of part of the reason is that they're synthetic. It eventually learns better and better what sort of the generating function was, and the generating function is simple and non-noisy enough that it gets better and better, and I think it would converge, but on fuzzy, noisy stuff like sentiment, it doesn't. Yeah?
Yeah, I was very pleased to see that you used the gated recurrent unit as the basis for this model. So why did you pick the one over an LSTM?
Simple answer, and I think it's generally the best answer whenever one of our researchers asked me, like, should I do X or Y? If you're really in the research, like at this sort of edge of knowledge, the answer is always both. And you should try both, and we tried both, and they worked similarly well, and one has fewer parameters, and that's all there is to it.
Okay, this is a perfect question while these guys knew around. I think there's something interesting in sort of sequence-based models versus the sort of memory nets, which aren't really kind of encoding along a sequence, but might have the positional encoding.
Right.
And I guess the summary that's in my head is when you show results, the sequence-based model is a fraction ahead of the positional memory nets, and when the Facebook guys show results, it's the opposite way around. So in my head, it's sort of basically a draw, right? So there's something kind of surprising. Like, it seems intuitive to me that having the sequence model and computing relations sort of write along the sentence and maintaining all this memory of everything you've read.
Right.
It seems like that should be way better, but in the current results, it sort of seems like it's basically a draw with the model that isn't doing that.
I think it depends highly on the task, right? So I think there are certain tasks where, like the John example, for instance, you just kind of need to know that John and like any location are in the same sentence, and if that's the case, then you can do it. I personally, philosophically, like the sequence models better because I feel like there have to be like you can always design a task where one has to fail, right? I say X loves Y, and I ask who is loving who, and then if you don't have a proper sequence model, it just any model that doesn't take the sequence properly into account has to fail. And so as long as I can come up with counterexamples that just like by definition always fail, I'm tempted to like the sequence models better.
Do you think the sequence models have problems which mean that?
I think they're harder to train. I think it comes down. That's my personal hunch. It comes down to an optimization problem of focusing on the right things and the right attention mechanisms. And maybe we need to have sequence models with smarter memories attached to them as you go over the sequence. And I don't know. Those are my thoughts.
Do you think that you need to have a sequence structure everywhere? For example, for the image, it doesn't seem very natural to have a sequential structure for the memory, for instance.
I don't think you have to, and certainly for the image stuff, we actually combine it with convolutional neural net too to extract some of the weights. And then you're right, it's actually not supernatural to go in most ways over those image blocks. So these two image blocks might be very related, but now the model has to learn to actually not pay attention to a couple of things and then again come in. Fortunately, the images are all the same size, and so it can actually learn sort of sequential patterns of like every 10 time steps you might want to look more carefully again or something like that. I do think sequences are very intuitive for a lot of things, right? Like a lot of the work on focusing on certain areas in an image can be cast as sequences. Language is very often for almost all people a straightforward sequence, certainly in speech, a lot of writing too. I like them philosophically, so I'm willing to sometimes go through harder optimization and more sort of tricks on the optimization to try to make them work. Oh yeah, sorry. I guess.
I was thinking about the multiple passes that you require in this architecture, and I wasn't sure if from a psycholinguistic perspective I can sort of justify that. And it seemed to me that if you're a very good speaker of the language, that you should be able to get it with a single pass. And so I'm just thinking about languages that I know of, but I'm not fluent enough to kind of do that inference. Whereby I would have to do this multiple passes as that system is kind of implied. What do you think about this?
About that? Yeah. So.
I'll just give you my intuition. If it were not for an upper resolution, that if you were to do with the example with the football, if you were to do it, going backwards, then probably you could stop, halfway through the passage and you'd get the result.
So yeah, you're right. I think if you had a perfect state that keeps track of all the stuff, then you could only do one pass, right? Now, that is only true in a sentiment example. I think if you, may I still have the slide. Let's say I gave you, let's say I gave you this story. All right, we'll just look at it here. Let's say I gave you these facts right here. I don't know if you can barely read them. It's just a bunch of facts. Sandra moved to the garden, Daniel went to the hallway, and so on. I asked you to read that whole story. Then I take it away from you, and then I ask you, where's John now? And I mentioned 10 names and 50 locations and so on. You'd also have to go back and start thinking, trying to find the facts that seem relevant. So you have to kind of reread the story with the new question in mind. So in that case, I think humans have to do it too.
So if the question is given in advance, then you can choose.
You read differently. Yeah.
Yes.
And that's exactly the intuition that we have here. Given the current question, let's go over the input and figure out what's relevant. But even there, if I have a very long story, I mention tons of different people, and then I say, by the way, John was always next to Mary. And you're like, oh, well, I just read 100 sentences. I didn't keep track of Mary because she didn't seem relevant because the question was about John, and only at the end I tell you John was always next to Mary. Now you have to go back and find facts about Mary. So I think there are certain examples where our memory capacity is clearly too limited to be able to do it in one pass. And then it's just kind of interesting to see that for some things where we still do it well, like sentiment, the model actually does benefit a little bit from it too.
All right, let's take speaker again.
Thank you.